Well, thanks very much. Thanks very much, Nosh, for the invitation to come here, and I certainly am glad to have been able to attend both these conferences. I think it's great to have this co-location of these two meetings between these two obviously overlapping communities, which have so many interests in common and so many complementary perspectives. And also, thanks for the nice introduction. So what I wanted to talk about today was some issues that try to maybe combine some concerns about network structure, some thoughts on network structure, with the issue of designing information systems in this kind of online social environment. In that way, try to combine several themes going on. It's actually, in a way, a bit daunting to follow this morning's session, which was completely fascinating and a lot of very interesting talks. And in a way, some of what I want to talk about sort of departs from ingredients of those talks. So, I mean, obviously, online social environments, I think, have led to this profound broadening of the design problems for information systems, right? So information systems where we have traditionally worried about issues like computational efficiency and scalability, we now overlay the kind of social feedback effects that happen when you try to design for an audience of millions of users. And so we're seeing these simultaneous complex social feedback effects coupled with the computational effects. And sort of one structure at the heart of this is the idea of an individual's social neighborhood, right? The node in the center being some user that you're designing the system for, and all these links out to all of their friends on some site, in this case, Facebook, to adapt this picture that Cameron Marlowe and his colleagues drew in 2009 of a Facebook engineer who donated his network neighborhood to science and allowed them to put this up there. This is the basic structure that one deals with for a lot of these applications. And here, really, I think, I mean, a lot of the intuition that, probably most of my intuition, and actually I think for a lot of the community, comes from work that people like Ron Bird have been doing, really sort of thinking about how network structure mediates our interaction with the rest of the world. And I think we see a lot of those ingredients here, right? So, I mean, if we think about some of the talks that happened earlier at NetSci, talked by my student Johan Ugander and by James and Lotta in this morning's session, thinking about this neighborhood as filtering information, and we see it has these characteristic structures in this joint work that Johan and I did with Lars Backstrom and Cameron Marlowe, for example, thinking about the different lobes in the social network, right? The lobe of coworkers, the lobe of old friends from grad school, and thinking about mechanisms of counting those lobes, the number of different ways you're plugged into the world as a means of quantifying engagement, for example. So that's sort of a basic framework that we can think about. Now, what I wanted to add to this was this idea that when we have these links are not all neutral, and they're also not all positive, right? So the language of the online world tends to have this very positive, put these very positive connotations on links. You're constantly connecting to your friends, your fans, your followers, and so forth. But of course, we have opinions about all these people. They can be positive or negative. And to invoke one of the central points from Michael Macy's talk this morning, influence, in turn, can work both positively and negatively, right? Some people we respect, we want to copy them. Some people we actually disagree with, we want to differentiate ourselves from them. And so how do we make sense of opinion and evaluation in a network context like this? And that, I want to be the starting point for my talk, and to offer some perspectives from work we've been doing recently on how to think about positive and negative opinion and what it might signify. Now, one of the issues here is that there are really lots of situations online and offline where people express an opinion about someone else or about someone else's content, and the intuitions that we bring to one domain may not apply in other domains. That's something that we'll see here, right? So what are some of the meanings that might get attached to the expression of opinion, right? Well, so on product rating sites, for example, like ePinions, there's the logo for ePinions. It could be I trust, right? So here's one user, they link to another to say I trust their reviews. I tend to agree with them, versus I distrust their reviews. Related, if you look at the political blogosphere, as far as I know, the political blogosphere has no logo of its own, so I've decided to nominate this as the logo for the political blogosphere from Natalie Glantz and Lotta Adamato's work. Right, we link people we agree with, we may link to people we disagree with. Similarly, other kinds of opinions that get expressed in a site that imposes community guidelines or norms for participation, sites like Wikipedia, for example, they do have a logo. For example, we can vote in favor or against admitting people into a community, and this will be another kind of opinion that will come up in this talk, right? So, in particular, on Wikipedia, something we'll be seeing later on, there's this very interesting source of evaluation data that you get, because if Wikipedia has this army of, a couple thousand volunteer system administrators who have great power on the site, they can help resolve disputes, they can lock down articles, they can arbitrate different situations that require some kind of active intervention. And obviously, with great power comes great responsibility, and one needs to actually be vetted by the community. So when you want to become a Wikipedia admin, there's essentially almost an academic tenure and promotion process. You submit your Wikipedia CV to the community, you say, I've edited this many articles, I've done this many good deeds, then there's a public discussion and a public vote, right? And so when someone in the community votes against your promotion, that's a vote that's public, recorded, negative, and consequential, and it therefore is something of interest to try studying. So there are many, many examples of this. There are obviously natural analogies in all of this to things in the offline world also. Okay, so with that in mind, I want to try walking through some of the different meanings that all of these might take, and some of the kinds of data we've looked at, and also some of the some theoretical models that one can build around this. I'm going to sort of fork this the discussion into two very different meanings of positive and negative. One based on agreement and disagreement, right, friend, enemy, and the other based on looking up versus looking down, right? So respecting someone versus not respecting someone. And argue these are somewhat orthogonal, and we should treat them differently. So there are theories in the social sciences to address each of these, the theory of balance and the theory of status, respectively. And I'll talk about some work we've been doing looking at both theoretical and empirical models of these. And then in the second part of the talk, I want to sort of investigate two broad themes related to the issue of status. I want to go a little deeper into status. One is some recent joint work with Cristian Danescu Niculescu Mizel, who's here at this conference, Lillian Li and Bo Peng, looking at how status and power differences are actually reflected in language usage, okay, in the way that people actually address each other, both offline and even online. And the second issue I wanted to look at with regard to status is the idea of status as an incentive. The idea that status-seeking individuals will behave in certain ways, and the community can thereby create mechanisms where, by seeking status, you do productive work for the community. An issue that shows up a lot in the design of crowdsourcing systems and has sort of deeper roots in the theory of the sociology of science. Okay, so let's try to run through those topics. Let's start with the theory of balance. So the theory of balance is about friend-enemy relations. It dates back, at the very least, to work of Haider in the 1940s, and then formalized in the language of graph theory by Cartwright and Harari in the 1950s. And their idea was to formalize the kind of wisdom contained in these proverbs like, the friend of my friend is my friend, the enemy of my friend is my enemy, and you can read all those. All of these are sort of old bromides that we can recite to each other. I don't want to get too much into the numerology of proverbs, but I will point out a few numerical coincidences in here. So if I think about this as a computer scientist, it's, the blank of my blank is my blank, right? It's sort of like we can fill in slots and memes like Lada was discussing in the morning. There's sort of three variable positions, and each of those could be either friend or enemy. So 2 times 2 times 2 choices. There are 8 proverbs I could have written down there. But some of those proverbs make no sense. Like, the friend of my friend is my enemy, right? Totally crazy. You wouldn't write that proverb down. Instead, I wrote down the 4 that arguably make sense. And if you think about the 4 that arguably make sense, they are the 4 where the word friend occurs an odd number of times. Okay. The other ones don't really belong up there. And that numerological coincidence, of course, makes sense when, like Cartwright and Harari, you draw these things as graphs, right? So these proverbs refer to 3-node graphs, A, B, and C. And you can declare certain configurations of positive or negative relations, friend or enemy relations on a triangle, as being either balanced or unbalanced in the language of balance theory, as to whether it's essentially socially or cognitively plausible, right? And so here, for example, we have plus, plus, plus on a triangle. That means 3 mutual friends, and that's viewed as balanced. That's a stable configuration. There's nothing that needs to get really worked out there. Similarly, a single plus with 2 minuses is, these 2 people are friends. They have a mutual enemy, and again, we think of that as a balanced structure. Things get more tricky when we look at the other configurations, right? So here we have A is friends with B and C, but B and C are enemies, right? So there's some tension there. There's some potential energy that needs to get worked out, because after all, it's in A's interest to try to get B and C maybe to reconcile, or perhaps failing that, A, turning this into a plus and making it balanced. Or maybe A will end up siding with one of them against the other, turning one of these pluses into a minus and making it balanced that way. And similarly, there's some latent inherent energy in this one, right, these three minuses, because opinions within balance theory differ on this, but I can certainly imagine situations, very high stakes situations, for example, a political primary where three people are currently opposed, but in the end, going into the general election, two of them are going to end up teaming up against the other one, right? The two who dislike each other the least will form some alliance, right? And we see that a lot. Okay, again, I should mention that balance theory is of two minds on this last triangle, right? There are certainly situations where it's a big world out there, and just because you don't like the person who lives down the street and the person who works at the store doesn't necessarily mean that they secretly are forming an alliance against you. Maybe there really are three minuses. One could look either way. But in these small group, high stakes situations, one often sees that. Okay, so balance here is really a theory of local consistency, how to impose local consistency in your relationships. But in a sense, the surprise, starting with Frank Harari's work in the 50s, is that balance is also a theory of polarization. At a global level, it results in these things breaking into two separate camps, again, like my Lauda's logo for the political blogosphere. That the theorem is, if all triads in a signed, so I have a signed complete graph. I have a graph where all pairs of nodes are connected, and I put a plus or a minus on each edge. Right? That's going to be my basic structure. And I look at every triangle in that complete graph. Right? They all look like one of these four things. If every single one of them is balanced, then it turns out, according to this theorem, that the only way that can happen is for the nodes to be partitioned into two sets. Right? Let's call them set X and set Y. Everyone in here is mutual friends. Everyone in here is mutual friends with each other. And everyone in between here, they're enemies. Okay? And so the idea is, obviously, in such a structure, all triangles are balanced, right? Every triangle is either entirely in here, or it has two people on one side, one on the other, and that two is a plus with two minuses. The non-trivial and really striking content of the theorem is that this is the only way it can happen, right? I should mention, obviously, one of these could be empty, so everyone could be an X, maybe. But if not that, then there are only these two groups, right? So it's really a theory of polarization. Now, one thing which is sort of a little surprising is that despite all of this work on balance theory, the question of dynamics was really relatively open until roughly 5-10 years ago, when it was really brought into focus by a number of groups, including the group of Antal, Kropivsky, and Redner at BU. Right? So the thing here, and this of course is true with equilibrium models in a number of domains in the social sciences, that it often describes an equilibrium outcome without a dynamics driving it there. Right? It doesn't propose the dynamics. Obviously, my description of all these was full of the language of dynamics. I said, well, if A doesn't like, if A is friends with B and C and they don't like each other, then there's this, potential energy that has to get resolved, and it's maybe going to lead here or lead there. That's a great story. But the theorem doesn't talk about that story. The theorem just says, if you should find yourself in a state of balance, here's what it's going to look like. So what could the dynamics look like? And so this was a question that a number of us began looking at, motivated in part by this work of Antal, Kropivsky, and Redner that really brought this question into the fore. And I want to tell you just about two dynamic models that we thought about. The first is a discrete dynamics, and that comes from their work. And this is some work that Seth Marvel, who's also here at this conference, and Steve Strogatz and I looked at in 2009. The idea is, one way to interpret the theory of balance is to say, you and I are trying to decide whether to be friends or enemies. To the extent that we agree on how we feel about third parties, we should be more friendly. And to the extent that we disagree on how we feel about third parties, we should be more unfriendly. Okay? So imagine A and B are trying to decide whether they should have a plus or a minus here. And they look at all the third parties they have relationships with. And this is a complete graph. So they have relationships with all third parties, right? We're thinking about, a small group of nations or politicians or children in a classroom, right? People where everyone knows and has an opinion about everybody else in this particular case. So A and B agree on how they feel about W, they agree on how they feel about X, they agree on how they feel about Y, they both don't like Y. They disagree on Z. So 3 agreements and 1 disagreement, so by a vote of 3-1, A and B should be friends. Right? Picking plus here creates only 1 unbalanced triad, which is less energy in the system. Becoming enemies would create 3, that'd be more energy in the system. So this actually is now at least a kind of energetic dynamics, which says we're going to keep flipping signs on edges to try reducing the energy. And the energy here is the number of unbalanced triangles. Right? And this rule says I'm going to flip my sign to plus or minus to bring down the number of unbalanced triads, which is reducing the energy in the system. I should mention that actually it's different from the kind of physical spin systems that one actually looks at in physics, because in physics, the spins are generally on the nodes. My friends in physics tell me that because here the spins, plus or minus, are on the edges of the graph, that makes it a gauge theory. And actually, they tell me even further that it's a Z2 gauge theory because it's plus or minus. But we don't have to worry about all that. The point is, this discrete dynamics creates an energy landscape. I didn't try to draw the energy landscape, which is very high dimensional, but it turns out to be extremely bumpy. And when you try this, the system gets trapped in numerous local minima on its way toward the ground state, which is complete balance, right? So if you run it in any kind of complicated starting condition, it's going to have a very hard time finding its way to balance. So some of this feels like, so maybe this is a rule that gets trapped a lot. Is there some other rule that manages to sort of glide past all those obstacles and find the bottom of the energy landscape? And it turned out around the same time, a dynamics was proposed that actually achieves that in a very elegant way. And this was some follow-up work that Seth, Steve, and Bobby Kleinberg and I did. A continuous dynamics for balance starts from the same picture, okay? And this was proposed by Kulikowski and his group in Poland in 2005. The idea is that let's imagine that the trick here is not to think about plus or minus, but to think about the edge weight between us as a number. Okay, so it's a real number, xij, the edge weight between I and j. And this real number can be positive, meaning friendship, or it can be negative, meaning enemy, but it's not just plus 1 or minus 1, it can slide continuously, which is going to give the system much more freedom to move around and avoid obstacles. Now, here's how these numbers evolve, okay, and this is going to be sort of my one slide with sort of some continuous math on it. The system evolves according to a differential equation, but I'll argue it's sort of an intuitive one, right? So let's go back to balance says, to the extent we agree on how we feel about third parties, we're more friendly. To the extent that we disagree, we're less friendly. So, okay, so I and j are deciding how to update xij. So they think about all these third parties k that they have relationships with. And they say, let's look at the product of our relationships with them, xik times xkj. How I feel about them times how you feel about them. They're both numbers. We can multiply them. If we're both positive, that leads to a positive number. And if we're both negative, that leads to a positive number. And if we have mixed sign, that leads to a positive number. If we have mixed sign, it leads to a negative number. Right? So when we agree, it pushes our value up. When we disagree, it pushes it down according to this differential equation. And we sum over everybody. And when you ran the system and you normalized the values so that they didn't blow up too much, you found that the system always, from any random starting condition, seemed to sort of glide its way toward perfect balance. Everything seemed to be sorting itself out. And we were finally able to actually prove that as a theorem, that this system actually is, in a sense, sort of the first dynamics we found that actually takes the Cartwright-Harari picture of this zero-energy ground state and actually finds a way to get to it from starting conditions. So the theorem is that for generic initial conditions, and if you keep normalizing the values, then in finite time, the system converges to each xij has a very simple form. And that simple form is, I take each node I, and I assign it a number y sub I. Okay? Think of it as that's their position on a one-dimensional spectrum. Okay? And the convergent value of xij is simply the product of yi times yj. So if you and I want to decide how we feel about each other in the limit of the system, you see where you are in the spectrum, you see where I am on the spectrum, we multiply those values. Which means if we have the same sign, we're friends. If we have opposite signs, we're enemies. Right? So left are all friends, right are all friends. So it's exactly this picture. These are all the negative yi's, these are all the positive yi's. But the system has to kind of, everything wends its way toward this, starting from a very messed up initial state. Okay. So we had this idea that there were these interesting structures with these balanced triangles, and we wanted to see the extent to which we could actually find this in online data. Right? So we needed to go to situations where people were evaluating each other online. And so we went to places that I mentioned on the third slide. We looked at opinions, where people can express trust or distrust. We looked at Wikipedia, where people vote for or against other people. We looked at Slashdot, where you can declare people as friends or foes. Effectively, we wanted places where edges were, we didn't have to solve the hard problem of manually coding how these two people felt about each other. There was a sign, right? There was a sign attached to the edge, and we could look at that. And so, but when we wanted to do that, we needed to reconcile the fact that this is not the only possible theory, right? So on the next slide, I want to mention a different interpretation of positive and negative evaluations, which is relative status. Okay? So this also comes out of work in the social sciences in the 50s and 60s and had been applied, for example, to product review sites in this influential paper of Guha et al. In 2004. And the idea is, on most of these sites, the link is directed. A links to B, but B might not link back to A. So we only know A's opinion of B. And that asymmetry might be important. It might be that when A links positively to B, A is saying, I look up to B. I feel deferential to B. B is higher status than me. And when A links negatively to B, A is looking down on B. A feels higher status. Okay. Now the point is, these are two theories, two very different interpretations of what link signs might mean. And they lead to different aggregate predictions. Okay? And so in some work that Yuri Leskovich and Dan Huttenlocher and I did, we looked at these data sets. And what we found was actually an aggregate tendency toward the status-based interpretation of things. Okay? So how does one distinguish between these two theories? Well, at a quick gloss of the methodology in this paper, if you look at certain triangles, the link sign that gets predicted is actually different between the two theories, right? So probably the most intuitive example is A links to B. It's this red edge, and we want to predict what sign that's going to have. And we know the signs of A to X and X to B. And we know they're both negative. Right? So balance theory would say that, well, A and B have this mutual enemy in X, so if they have a mutual enemy, they should be friends. I mean, if we're talking about political opinions where I know that A and B both strongly disagree with a liberal blogger, maybe they really both are conservative bloggers. But if I'm thinking about a product review site, it says that A doesn't think very highly of X's expertise on digital cameras, and X doesn't think very highly of B's expertise on digital cameras. And so maybe, in fact, A looks down especially strongly on B, right? Because A is above someone who's above B. And in fact, we find that much more strongly in all these online data sets. There are other predictions that status makes that are even a little harder to believe initially, but actually are also borne out in the data. And again, these are all in aggregate, right? Any individual triangle shows up. The question is how it deviates from this prediction. So for example, if B is positive to X and X is positive to A, balance theory finds this very easy. They have a mutual friend. They should be friendly. Status doesn't think of it that way. Status would say, well, B looks up to X, X looks up to A might be as actually negative, right? And you can, again, see intuition for that, right? That, again, if we imagine sort of an academic situation where we're listening in on some hiring meeting where B is saying we should really try to recruit X because they're a real star, and we go and we listen in on a hiring meeting where X is saying we should try to recruit A, they're a real star, and then we try to find out what A's opinion about B is. Well, A would probably be polite, but maybe A would actually look down on B. Right? That's what status would say. So, and again, we find that in the data. In aggregate, there's a tendency that the negative edge is overrepresented relative to the data. Now, I should mention a couple things here. One is both of these are going on, and actually, I think there are some really interesting open questions that get churned up by this kind of analysis, because you actually, in a sense, see both status and balance at work, and they're applicable in different parts of the network. So in particular, many of these links, as I said, only go one way. A links to B, B doesn't link back to A. But in the parts that are reciprocal, where each expresses an opinion about the other, there's more of a tendency toward balance than there is in the rest of the network, right? Making us imagine that perhaps something is happening where these networks are being used, right? They have mixed uses, and when it's for mutual reciprocal relationships, the logic of balance is at work more strongly, whereas when you're referring to people that you don't really know that are sort of have this asymmetric relation, then the principles of status may be more dominant. I think it also has this interesting design implication, which is that we have these sites where user A is being asked to express their opinion of user B, right? And there's a button, yes, no, plus, minus. And, and user A attempts to reason with the system that, no, actually my feeling about them is this sort of complex, nuanced thing, and the system says, no, plus, minus. Those are your two choices. Right? We've collapsed everything into this one dimension when really there's at least these two dimensions that balance and status suggest to us. The difference between I agree with you and I respect you. Okay. I'm suddenly discovering I could go into slideshow mode and make this all a little bigger. Okay. So, right, I agree with you, balance theory, I respect you. And to the extent we could separate those out, right, it's possible to agree with people you don't respect and to respect people that you don't agree with. To the extent we could actually find mechanisms to separate those into their two components, I think that would actually be an interesting kind of design issue. Okay, so we did a number of things with this. We built machine learning models, which actually led to a number of interesting further thoughts. One of them was some of the subtle ways in which status is operating on these systems. So let me show you one slide which has remained something of a mystery to us, although we're making progress on it. Okay, so one of the subtle ways in which status operates. So here's what we thought to ourselves. Let's take Wikipedia voting. And so again, remember that voting for adminship means that someone comes up for promotion, they want to be an admin. It's like a tenure or promotion case. And so the community votes on them, positively or negatively. Now we thought we could infer status from these triangles, but on Wikipedia there are raw measures of status, such as how many edits you've logged in the system, right? I mean, so by the time people come for promotion, they've typically logged something on the order of 10,000 edits to Wikipedia across all articles. These are people who have spent a lot of time on the system. And so let's think of that as a kind of achievement level, or at least a contribution level, and ask, that's certainly some kind of absolute proxy for some sort of status. How does my chance of voting positively on you relate to the difference between the number of edits I've made and the number of edits that you've made, right? And you would think that if that difference is, let's see, negative, I'm lower, then I'm looking up to you. You've done a lot of edits, way beyond what I've done, and so I'm going to be more likely to vote positively. Whereas if that number is positive, I have a lot more edits, I'm looking down on you, maybe I'm more likely to vote negatively because I'm not sure you're really qualified. And so we plotted that. That's a very simple curve, right? So this is the baseline. 78% of all votes on Wikipedia are positive, because after all, negative votes are very costly, right? You've just created a relationship where someone is really not happy with you, right, when you vote negatively. So a lot of them are positive. But if what we're thinking is right, this curve should go down. And so we plotted this curve. You know, you do it from the data. And at first we were very happy to see that it went down. And often when Dan, Uri, and I are looking at data, we're sometimes a little slow on the uptake. So probably for the first few weeks, the main thing we noticed was, you know, down. That's good, right? And we did it for Barn Stars, which are these awards, these badges you can get on Wikipedia, and again, tendency down. And after a couple of weeks, we noticed what was, of course, the much more interesting feature of this plot, and maybe you've noticed it already, that it doesn't just go monotonically down. There's this local minimum here. And the local minimum is right around a difference of 0. Okay. Now, that's sort of a mystery to us, right? Because we can debate what that means, but let me sort of interpret it literally. What's the data saying? It's saying that voters, right, Wikipedians, are particularly harsh on people whose achievement level is exactly the same as their own. Okay? When someone is exactly like you, you're more likely to vote negatively. And then as the difference becomes positive, somehow there's this rebound. And somehow now the chance of voting positively is a little higher. So we thought about this, and there are obviously a number of interpretations that you can impart to this, right? You know, latent competition, a sort of sense of increased understanding of their limitations, all sorts of things. With Uri's student Ashton Anderson, we tried to look at sort of how to disentangle this into its constituent parts. And I don't assert that we actually now understand why this is there, but we at least have tried to sort of resolve it into a sequence of effects that are being combined to produce this. And the combination of effects that we wanted to do was to separate this based on similarity between users, right? So when I go to vote on you, we have a difference in achievement level. We also differ in many other ways. Let's look at, in particular, differences based on our similarity in what we edit. Okay, so similarity in what we edit, we could be in the very similar areas, we could be in very different areas. And does that affect how we vote? And the answer is actually yes. So 3 curves. So I'm going to take this curve, I'm going to break it into 3 curves based on whether the voter candidate pair has very high similarity in what they edit, medium similarity, or low similarity. Okay, just based on the articles they've chosen to edit, right? So am I, you know, someone who edits articles on, you know, matrix computations, and I'm voting on someone who does, you know, spectral algorithms? We're very similar. You know, if I do matrix computations and I'm voting on someone who does Moroccan cuisine, I don't know much about Moroccan cuisine, and we're very different. So these are the 3 curves. And okay, first you notice high similarity, you're more likely to vote positively, medium, and low. But the other is, each of them is now much more approximately monotone. That dip in the middle sort of went away. So where did it go? It was here, but each similarity level is gone. It was actually sort of monotone. Where it went is the differential participation of people based on their similarity, right? So there's a selection effect going on here. If, and this is what's happening here, based on the status difference, right? So when I show up to vote on you, if I'm much higher status than you, you have to ask, I'm busy. I'm off editing my pages on matrix algorithms or Moroccan cuisine. I don't, you know, I'm logging my 30,000 edits on the system, yet I showed up to vote on you. Why did I do that? Well, it turns out the people who show up to vote when they have higher status are more similar. Okay? Right? They're more similar and more positively disposed. So what happens is a candidate comes up for election. They get a mix of people at sort of lower and equal status levels. And they get this infusion of higher status people who are skewed to be more similar. And so essentially, as you combine these three curves, you're not averaging them with equal weights. You're averaging them according to something that looks like this. And so you sort of jump from a curve that's averaged like this, and you jump up to this curve because it's enriched with high similarity people. Right? And that essentially seems to be what's at least helping to produce this rebounding effect, this dip in the middle. It's this sort of differential selection of sympathetic, high-status people who show up as part of this thing. But again, I think there are a lot of ingredients going on here, but this notion that status can be this complicated, non-monotone effect, I think remains a very, very intriguing question. Okay, so I want to jump from here into two sort of larger issues. Maybe spend about sort of 10, 15 minutes on each one, and then wrap up. One is, again, language and online networks and status. Right? So trying to add language as a feature to all of this, and I'll motivate that starting next slide. And then I'll move on to this issue of status as an incentive in the design of these systems. Okay. So language, right? So adding language to these systems, I think, is an enormous opportunity. There have been workshops going on at these conferences that also mention, this big opportunity. Because if you think about it, we start with a picture like on the first slide of just a graph. And the graph is very impressive, and it has a lot of rich structure. And gradually, we begin adding annotations to it. We add pluses and minuses. We add timestamps. We add tie strengths or edge weights. We add periods when people were in contact. We do all those things, and those things all tend to have the form, their numbers, their sign bits, because our algorithms can handle those. But really, what's transiting these edges often is text. What's actually flowing across these edges is communication in free text. And I think the sort of fact that we've been maybe, as a community, slower to develop a sort of wide array of techniques for this is simply because it's much, much harder. I can't just take a numerical edge weight, a numerical timestamp. I have to actually do some processing on the text that's flowing across this. And so there have been a number of groups, obviously, that have been interested in doing this. I want to talk a bit about this collaboration that I did with Christian and Lillian and Boal, which appeared at the WWW conference this past year. The idea was, can we detect status or power differences from the language that people use when they talk to each other? Right? If you were looking at this, can you guess which of these people have a kind of equal mutual relationship, which people have a status plus relationship or status negative relationship? Right? How does that work? Now, there have been a number of approaches to this. Some work in the natural language processing community, for example, looked at domain-specific features where you take something like the Enron corpus, all the email among Enron executives which entered the public record, and you look for phrases that are highly correlated with a status difference between the sender and recipient, right? So things like collectivist language suggesting a superior telling a subordinate to do something, things like that. We were interested in more domain-independent measures, things that work across domains using this principle from social psychology known as language coordination. Okay. So let me spend a slide telling you what language coordination is. And here I'll adapt an example from two of my co-authors, Christian and Lillian, who showed actually that language coordination not only takes place in everyday life, but even in the screenplays of films. Okay, so we can take many examples. This is two characters from the movie The Getaway, 1970 movie. This is Steve McQueen, that's Ally McGraw. The guy on the left says, "At least you're outside," and the woman on the right, Ally McGraw, says, "It doesn't make much difference." Okay. One thing you notice here is, so he expressed, "At least you're outside." The idiom he uses has a quantity in it, least, right? And she responds with her own idiomatic construction, which has a quantity in it also, much. Right? So he uses a quantifier, she responds with a quantifier. Okay? And that, in a sense, as formalized in social psych literature, is sort of the crux of what language coordination is. It's the unconscious imitation of function word choices, right? Prepositions, articles, conjunctions, and quantifiers, and many others. When you say something, right, if you're speaking to someone who uses a lot of prepositions, you gradually, subconsciously, and almost immediately start upping the number of prepositions that you use in your sentences. This is clearly happening at some kind of latent level because, after all, I mean, how many prepositions did I just use in the previous sentence? You don't know. I don't know. it's this low-level channel, right, that's happening. But it's actually, the surprising thing in these studies is it's actually present. And I'll show you some things that show it's present to a statistically significant extent. And the point is, right, she didn't have to use a quantifier here. She could have said it doesn't really matter. She could have said it's not really important. But she said it doesn't make much difference. And that's the kind of thing that you see. Any one of these is, of course, coincidental. But in aggregate, you see an effect there. You see that people are echoing these seemingly irrelevant, certainly information-wise, almost irrelevant function word choices. And this clearly is part of a broader phenomenon of coordination, right? That if you cross your arms, then your conversational partner might subconsciously cross their arms. You nod, they might nod. All of these things are other dimensions on which we coordinate. But the question is, can we see it even just in word choices? So our hypothesis, and this was implicit at very small scales in some of this previous work, we wanted to sort of see if it was actually a feature that would work in some of our data, that when there's a status or power imbalance, that the low power person is going to coordinate more, and the high power person will coordinate less. Okay? That the status difference will be reflected in a coordination difference, and the lower person is going to try to climb uphill more than the high status person comes downhill to meet it. Okay, that was the idea. Now, if we want to do this at a large scale, we need actually an algorithm to measure coordination. And my co-author, Christian, whose work really was sort of the original work in 2011 that brought this idea of language coordination into these online data sets, he had this proposed measure for how to tell if coordination is happening. So the idea is A and B are talking to each other. When A uses a word of type T, a preposition or a quantifier, say, does this raise B's chance of using it in the very next utterance? Now, what we need to do is control for the base rate at which B uses prepositions in general. And not just that, but the base rate at which B uses prepositions when they talk to A. Right? Maybe when A and B talk, they always talk about how they're remodeling their apartment, and there's lots of things about I put the vase on the dresser behind the door, you know, lots of prepositions. They always do that. But we're interested in the kind of instant priming in which does B use this type T in the very next utterance after A uses it. Right? In the same way that it was used in the very next utterance here. So that's going to be this difference in conditional probabilities. What's the probability that B uses a preposition given that A used a preposition in the very previous utterance minus the probability that B uses the preposition just when they reply to A in general? Okay? So if that difference, and we'll take these are going to be small differences, right? We're going to take those and multiply them by 100. So it's going to be like a percentage, a sort of absolute percentage difference. If those numbers are positive, then you see a coordination effect. And if they're 0, then you see nothing. And otherwise, you might actually see anti-coordination if they're negative. So we'll plot some bar graphs. We'll see if the bars go up, showing positive coordination. So one data set you can look at, if you want sort of carefully transcribed speech with clear power differences, one place we went and looked actually was, as a way to sort of test out some of these ideas, transcripts of oral arguments before the US Supreme Court. So you transcribe those. There are lawyers talking. There are justices talking. There's a very clear status difference there, a very clear power difference. And this is actually what you see. So let me walk you through this plot a little bit. These are sort of average measures. We have quantifiers, adverbs, conjunctions, articles, and so forth. These bars could go up or down, right? This is the sort of probability difference normalized on the scale to have integer units, or at least larger units. Right? And so these bars could go down as easily as they could go up. If people are anti-coordinating, those things would all be pointing down. But the point is they're all pointing up to a statistically significant extent. Right? So there is coordination going on, and seriously so, when people are addressing each other on the Supreme Court. Right? Lawyers talking to justices. And secondly, there is a significant difference in how much the different parties are coordinating. Right? So when lawyers talk to justices, that's the purple curve. Those bars are very tall. There's a lot of coordination going uphill on this status gradient. When justices are talking to lawyers, there are lower bars. There's less coordination coming downhill on the status gradient. Okay. And we see that across all the different parts of speech types as well as when we average them all together. Now, of course, when you're in a situation like the Supreme Court, there's lots of stuff happening. People are crossing their arms, they're leaning back, they're standing up straight. There's a lot of nonverbal stuff happening. On Wikipedia, by contrast, when people are coming up for, say, adminship elections, they become admins, all that is happening through typing, right? You know, I'm coming for promotion, and you say, I don't like how you deleted that article, and I think you should have engaged more input from all parties concerned, and that was bad. And then you have to answer it because you're running for election. So you type back, well, no, it was because whatever. And it turns out, even there, you are coordinating to their function word choices. Okay? Even though you're not seeing them, you're not interacting with them in real time, And so we looked at how this works, and in particular, unlike the Supreme Court, where there are these fixed, rigid status roles. Let me go back to that for a second. On Wikipedia, people actually get promoted. They become admins, right? So the very same person with all their very same personal traits was once an admin to be, running for election, and later they become an actual full-fledged admin. And you could ask, how does their level of coordination change when they go through that transformation? And how does the world's coordination to them change? And in fact, it goes exactly like these hypotheses would suggest. So this is, the red dot line is when they're the target of speech. So this is the moment they got promoted. Here is the previous month before they got promoted. How much is the world coordinating to them? They got promoted. And here's how much the world is coordinating with them 1, 2, and 3 months afterwards. Right? You notice there's sort of a first month when this newly promoted person is still sort of your buddy, your equal. But then gradually there's this sort of adaptation that, no, they're actually now in a high status position. The coordination is going up the second month in. And similarly, they, in this sort of power corrupts kind of thing, right? They start up here, but after a while, they're actually down here. They're coordinating less as they settle into this new role. Okay? And there are a number of other things going on here, which are quite subtle, which I won't have time to go into. In particular, people who are coming up for promotion, the ones who succeed already had higher coordination levels than the ones who failed at being promoted. And the ones who failed, actually, their coordination moves inversely. They actually start to coordinate more after an unsuccessful promotion attempt. So there's actually lots of things sort of wrapped up together. The last thing I want to say about coordination, and then move on to status as incentive, which will be my last piece of this talk. Last thing I wanted to say, this is all about fixed notions of status, right? You have high status, you have low status. But as we know from things like social exchange theory, dependence can create a kind of power difference also, right? So at the moment when you're, say, running for election in Wikipedia or elsewhere, you're dependent on these people to like you. That creates a power imbalance where you're lower down. The same thing you could argue happens on the Supreme Court. If a lawyer is arguing to a justice who is ultimately going to vote against them, right? A lawyer trying to argue in favor of the healthcare bill is arguing in front of Anthony Scalia or somebody who is obviously widely expected to vote against it. There's a power imbalance. They're working extra hard to try and convince them. And if they're arguing for a friendly justice, maybe there's less dependence. Do we see that in the data? And the answer is we actually do. So here we have these same kind of plots, right? They all go up because there's coordination. This is lawyers talking to justices, both bars. The purple is they're talking to a justice who ends up voting against them. And the green is they're talking to a justice who ends up voting for their side. Right? And again, there's a significant difference where they're coordinating more to the people who end up voting against them. Right? Just kind of working harder. And actually you can flip that around, right? Because if there's a bigger power gradient, we should see that from the justice's side also, and we do. That a justice who's going to end up voting for the lawyer is coordinating more with them when they talk. A justice who will end up voting against is coordinating less when they talk to them. So again, it's this notion that language coordination, which is clearly escaping our conscious perception, is present, and it's almost like this sort of invisible radio frequency that once you tune the dial into it, you suddenly start picking it up. And when you pick it up, you notice things like status differences. You notice things like who ends up being positively disposed toward whom. And overall, I think it's a very interesting kind of numerical reduction of a bunch of very messy language data to try learning something about the dynamics within a group, even if we just have online transcripts of their conversation. Okay. So I want to do one final thing here, which is this has been about sort of observing some of these systems, how they operate. But in the end, we also want to design these systems. And designing them involves building in incentives. And when I think about sort of incentives for achieving status, one can think about the online world. I also inevitably think about the scientific community. And you might have noticed that my talk, because I'm an academic and somehow can't escape that mindset, is sort of loaded with analogies to the academic world, right? Wikipedia is like tenure and promotion, and high status, low status is like the academic hiring process. But those analogies are, in a sense, genuine. And we could turn that around and ask how some of these ideas may help us think about how science actually gets done, right? Because in a sense, science is this massively crowdsourced kind of activity. So evaluation obviously is present all across the scientific community, right? You in this little gloss here, you get NSF funding to do your research so it can appear in Science and Nature, so you can receive a Nobel Prize in sort of cartoon form. All of these things, funding and publication and prizes, they're all ways of conferring status on people. And although it's decentralized, to some extent, science is sort of a planned economy, right? Committees really do sit down and try to decide who's going to get funded. They sit down and decide what papers will get accepted. They form prize committees and decide who gets prizes. They are trying to actually articulate priorities for the area. Right? And so obviously these show up in online crowdsourced systems, but you would argue they also show up in this massive offline thing that we call science. Now, I started thinking about these analogies actually when I got approached by members of my own community, the computer science community, with a manifesto that they wanted me to sign. I won't read the manifesto to you, but it essentially was arguing that certain areas of computer science they felt had lost their way and were working on questions that were too technical and too incremental and not thinking about the big important conceptual things. And that essentially the wrong papers are getting accepted, right? If you get any 3 or more scientists together and let them talk, within 10 minutes they'll start talking about how the wrong papers are getting accepted. It's sort of a pathology of how scientific credit is allocated that everyone is sort of fascinated by. And this was sort of a manifesto that people wanted to sign on to, trying to formalize that in a particular context. So this was the question I was interested in, right? So if status is serving as an incentive, and we therefore are very energized about the fact that it's being assigned unfairly, can we sort of dissect the different unfair ways in which this is actually happening, right? What are the unfair ways in which people actually acquire status? So you can sort of recognize 2 maybe. One is what this manifesto was actually about, which is that certain research questions seem to receive an unfair amount of credit, right? So there's lots of questions out there. Some of them are very important. And paradoxically, the important ones are being worked on, you feel like, less than they should. And instead, everyone's getting all this credit for doing things that are more technical and seemingly more narrow, right? It's often wrapped up with this issue of technical difficulty. On the other hand, there's, of course, a second kind of pathology. In a sense, the sort of one that's been studied for a longer time. It's Robert Merton's celebrated Matthew effect from 1968. Most of you probably know where the term Matthew effect comes from. It comes from the sentence in the book of Matthew from the New Testament of the Bible, which roughly says that they who already have a lot get more, and they who don't have very much lose even that. That when 2 researchers make a discovery, say independently or jointly, often the more famous one gets more of the credit, and the one who is less famous gets less of the credit, right? So it's often referred to as, so-and-so's result, and that person was the famous one. Right? That's the Matthew effect. You can actually think of these as sort of 2 sides of a coin, and I mean that sort of literally, because if you think of science as a matching up of people with problems to work on, then this is operating on the problem side. It's being unfair in how you evaluate problems, and this is operating on the people side. It's being unfair in how you evaluate people. Right? Okay, so maybe this is just yet another story of how inherent human biases are leading to unfairness, but if it's such a robust phenomenon, you wonder, is there something more going on here? So this gets to the point that credit creates incentive, right? People seeking status are following the trail of an incentive system trying to lead to a certain outcome. And a number of communities have looked at this, right? So the philosophy of science, economics of science, economic theories of research and development. I mean, there's a number of people who've written about this. One sort of very eloquent phrasing of this comes from the social philosopher Pierre Bourdieu, right, who wrote about how researchers' motivations, and of course as scientists we all recognize this, organized by reference to conscious or unconscious anticipation of the average chances of profit. So they concentrate on problems regarded as the most important ones, but then there's this intense competition triggered off, which brings about a fall in the chance of you getting credit for the important one, and hence a departure of the fraction researchers toward other objects which are less prestigious, but around which the competition is also less intense, right? So big problem, big competition, hotspots, people get scared away from the hotspots, move to other things. Sort of looking at it as a computer scientist, for a social philosopher, it's a remarkably apt description of load shedding in a distributed system, right? There's too much happening here, we need to shed the load elsewhere. Okay, so my student Segal or Ren and I thought, this is concrete enough we could really sort of look at this as a mathematical model. And so I wanted to sort of end with one final model here. And that actually, we started building this model. We discovered actually it was similar to work by Philip Kitcher in the philosophy of science from the 90s, although his model had a bunch of extra features that we didn't really need to try addressing the points we wanted to address. So let me focus on this more streamlined one. So scientific research, we're thinking of as sort of a 2-sided market, right? There are researchers on the left, A, B, C, D, and there are projects on the right, X, Y, Z. And we're going to take a very, very simplified view of things. We're going to imagine that these are sort of open math problems, right? They're sort of challenge problems. And so you as a researcher are simply going to decide, I'm going to work on this problem. And when you work on it, a conceptual coin gets flipped, and you either succeed or you fail. Okay? So here we have researchers picking problems. A and B pick X, C picks Y, D picks Z. A coin gets flipped for each of them, whether they succeed or fail. If two people succeed, well, the one who accidentally did it first is going to get the credit, right? So you don't necessarily get the credit if you succeed because you might not have succeeded first. Okay, so projects have two parameters. One is a weight, x has weight, wx, which means that's the importance. Higher weight, more important. It also has a difficulty, right? So f sub x is think of it as the failure probability. F sub x is the probability that if you try this, you will fail. So large number means high chance of failure. Okay. And I need one more piece of notation, which is for project J, K sub J is the number of people who choose that project to work on. So Kx is 2, and Ky and K2 are 1. Okay, so this is a very simple model, and as a result, we can talk about it almost sort of completely from start to finish. So society wants important projects to get solved, right? So from society's point of view, we don't care how the researchers divide themselves up. Let's just see some important work get done. And so the welfare to society is simply the sum over all projects J of the importance of J times the chance it gets solved. And the chance it gets solved is simply 1 minus the chance that everybody who works on it fails, which is that. So this is the expected gain society gets from that project, and we sum it over all J. That's what society cares about. But that's not what a researcher cares about. If a researcher picks project J, then what's their expected benefit from that? Well, this is the chance it gets solved times its importance, but there were KJ people on it, so there's a 1 in KJ chance that you're the one who solved it first, got the credit. So that's your payoff. Okay. So in a way, we've now actually, somehow by just picking all these different parameters, we've defined a game, right? In the sense of game theory, it has players, it has strategies, what do you work on? It's a simultaneous move game, and it has payoffs. Once we all choose our project, some coins get flipped, and we get these payoffs, and society benefits them. Okay, and so it's natural to ask about the Nash equilibrium of this game, one in which even after, say, public announcements were made about choices, no one would have an incentive to change projects. Okay, so let me show you an example of this game. Right, so this is a world with 2 researchers and 2 projects. I just want something very simple so that we can see what's going on. On the left here, so this project has importance 1, difficulty half. This has importance 9/10, difficulty 2/3, which means the lower one is less important and more difficult. Okay, so on the left we have the unique Nash equilibrium. Both players try x because x is easier and more important. They're hoping to get the credit even though they have to compete for it. And so this gets solved with probability 3/4. Your chance of actually getting the credit is a half because you're competing. So your payoff is 3/8 if you work through it. Whereas if you switch to this, right, if you follow Bourdieu's suggestion of let's avoid the intense competition and move to something else, you'd have to pick this problem. And then you have a 1/3 chance of getting 9/10 of a unit of credit. You only get 3/10. You don't want to do that. So people are piling up on this. But that's not optimal for society. Optimal for society, and I'll skip the calculation here, which is easy, is if we worked on separate projects. Because then you would get a half in expectation from the first, and you'd get 3/10 from the second, and that's bigger than 3/4. Okay? So that's fine. That just is yet another example of a game where the Nash equilibrium is not socially optimal at half point. But here's what's interesting. Suppose you were in charge of the world, right? Could you actually do something about this? Right? After all, it's sort of, these problems have whatever importance they have. But in fact, you could, right? Just because this is the importance of the problem, just because everyone agrees that's the importance of the problem, doesn't mean we actually have to have that be the credit we give it. Suppose instead that we all got together as a funding agency or a conference program committee or a prize committee and decided we all agree that this is really 9/10 of importance, but let's assign it credit of 6/5. If you solve this problem, you will get 6/5 of a unit of credit. Well, suddenly the equilibrium changes, and it changes to something which is now socially optimal. Right? You have made this problem sufficiently enticing that this person now does depart and actually go work on it. Okay? And so, effectively, what's the point? To optimize the collective productivity, the community needs some kind of internal accounting mechanism for credit that's actually different from the actual value of these projects. It's not like we suddenly forgot that this was the less important project. We just all chose to pretend that was not the case so as to achieve social optimality. And I can do that on the other side also. Right? So this is this unfairness on the project side. We can also see something sort of like the Matthew effect. I could announce instead, I'm not going to rig the credit on the project, I'll simply announce that although A and B are identical researchers, because A maybe graduated from a more prestigious university or has some other kind of, for some symmetry breaking reason, if you both work on this and you both solve it, then A is going to has a 5/6 chance of getting the credit, and B only has a 1/6 chance. Well, then again, B no longer sees it as worth competing, and so they will depart to this project. Okay? And so by breaking the symmetry, you allow A to sort of move without regard to competition, and you force B to, right? So it's not fair. In fact, it's sort of grotesquely unfair. It says by arbitrarily marginalizing certain people in the community, you've actually forced them to embark on higher risk courses of action, which are overall benefiting society. Right? That's the message. And so these are just a series of examples, but I'm skipping the sort of theoretical part of this work, which is actually a theorem that says for any set of players and projects that you set up this way, there's always a reweighting of the projects or a reweighting of the players so that you can achieve social optimality. And typically, that will be a rather unfair reweighting of things. Okay. And I don't have time to go through all of the math. I just want to show a picture to point out that, in fact, although you can almost see a network starting to emerge here, right? But it's not the network you quite thought. It's the sort of matching market of people to projects. And the way you end up proving this is actually to go back to a very different literature on traffic congestion. And say, really what's happening is I have players and projects. I'm going to build a bipartite graph between them. I'm going to imagine that the players are all actually trying to route their way through the network to this. And effectively what they're doing is congesting these links. They're creating congestion which is socially suboptimal because too many people are working here. And this unfair allocation of credit is effectively acting sort of like a toll. And so if this were a road network, I'd be putting a toll here to scare people off. And the analog of that toll in the scientific community is this misallocation of credit, which is causing people to drive on some other route and thereby uncongest the highways being the project. Okay? Okay. So I wanted to wrap up. There's actually a lot of things one can do even just with this model. In particular, looking at heterogeneous players, looking at things like collaboration, like sequentiality in time, limited information, all these things that obviously would be interesting to layer on. But I want to wrap up here and just sort of come back to the top level message and think about it, which is opinion and evaluation is really, there are many signals and many channels along which we interpret it, and in turn it is serving many different purposes, right? Sometimes it means agreement or disagreement. Sometimes it means high or low status. The channels along which we get it are both network linking, they're language information, they're even implicit information about your choice of what to work on in a giant crowdsourced environment. And so I think what's interesting here is that given all these multiple dimensions, often the signal we can extract from things like asking people to evaluate each other is quite an impoverished signal. And one notion here really is that maybe some of the understanding of the many dimensions of status could actually help inform better ways of eliciting this information, feeding it back into the design process, and in the process of doing that, to think about the kind of incentives that are being generated, right? And whether the incentives created by opinion and by status are causing the right kind of work to get done in many of these systems. So I think overall, it's really an opportunity to understand this wide range of forces. It's going to involve ideas from networks, ideas from both collective human behavior and psychological issues. And overall, I think it's going to provide a very rich set of questions as we move forward in this area. Thanks very much.